Hello, John McCardle here, and everything goes better with practice, right? So I have this presentation tomorrow. This is going to be my time check and my backup in case the demos don't work on the other side of the firewall. So let me jump right into it. This is a presentation on encoder-only processing. I know there's a lot of buzz with generative models like ChatGPT and all the shenanigans that has spawned on the internet. But I want to focus on things that are small, fast, and don't generate, but you can still get a lot of answers out of them even without generating new text. Okay, let's proceed. So what's an encoder? An encoder is a model that transforms text into a dense numerical representation. We'll go into those representations in a second here. Generally speaking, this means we take a whole block of text all at one time, whether it's a sentence or a paragraph, or in the case of modern BERT and the larger encoders, whole documents at a time, multiple pages. And we create a single vector out of this. And that vector can be compared, added, subtracted, multiplied in much more straightforward ways than the text itself could. So other advantages of an encoder is that it's deterministic. You give it the same text in, you'll get the same encoding out every time. And task specific, these guys are kind of the OG for pre-trained. The idea is that you can very easily add a small task specific head on top of the encoder that will immediately benefit from all of the language understanding the base model has and be overall quite small and quite fast to train for whatever specific task you want to specialize in. So I'm going to talk about these 5 domains. And some of them are pretty quick. Some of them have a lot of cool demos, so let's get cooking. First, we'll talk about transforming text into dense. I want to talk about the old days a little bit. This isn't a super technical in the weeds demo, but what you can use as an alternative to the dense representations that encoders make readily available to us is sparse representations. Sparse encodings are a one-hot encoding. These mean slightly different things, but a one-hot encoding refers to a single one in a vector, a tensor, or an array. That is all zeros except for one hot value, one turned on value. And this means like the word is present in the vocabulary. Every vocabulary item, so if you have 50,000 words that your model knows how to understand, that's 50,000 is the length of this representation. And you just turn on a single value to 1 when that word appears. And this is, it seems kind of insane, but this is literally how old school Google worked. It just marked which words are present, and from that we are able to make all kinds of downstream representations, like add up all the represented words in a document or divide it by how important that word is across the entire corpus. And you might get something that has 50,000 dimensions, but it's no longer a one-hot encoding. It has higher values or fractional values that represent more things, like importance or significance. And those are very valid techniques that we still actually use, and we like to pair them with the encoder techniques I'm going to spend the rest of this talk talking about for Search Fusion. But I just want to give that as background. This kind of non-dense representation is kind of what encoders provide us an alternative to. And dense representations aren't just stranger than you suppose, they're stranger than you can suppose. They may have 384, maybe 768, maybe 1024 dimensions to them. Every dimension is going to have a different value, and that's why it's called dense. Every value in the vector is considered to have a significant value. You can't just erase one of those dimensions. You would lose a lot of semantic importance. And I think what's important to take away here is that we're not giving it meaning for these 768 different dimensions. the model is learning those meanings during training. So that means we could not tell you what the third or fourth or 18th value in this vector means. And in fact, it doesn't really make sense to even look at them individually as different dimensions like that. It's more that we need to take a basis out of this embedding space and say that it's the different directions, not the individual elements of the embedding, that start to have meaning. So if a word has like gender, like king and queen, those have a kind of commonality on royalty, but a difference in male versus female gender. We might expect to see in the embedding space that the model learns that king and queen differ by the difference of adding or subtracting man or woman. And we don't always have exact matches there. It can sometimes reveal like bias in your data set, or just bias in the base language that you're studying when you find things that do or don't add up like that. It's very interesting. It's kind of telling us things we weren't expecting to learn. And this very idea of converting text into a dense representation, I really think is like, it's the silent breakthrough that has really not caught on. Like, generative AI is very exciting, but dense embeddings are just such a complete shakeup of how we understand language that I don't think we've really grappled with the entire meaning of them yet. But I'll save that for a later rabbit hole. And mostly everything we talk about encoders is going to be in terms of BERT. It's bidirectional encoder representations from transformers. And I couldn't tell you exactly why. It was just a particularly successful BERT. And what you'll see is now BERT, the all caps BERT, is a part of the naming convention for all the other progeny of BERT. And a lot of encoder models are just fine-tuned away from BERT, or a lot of classifier heads were trained on top of BERT. And the bidirectional part is probably the most important thing to distinguish this from generative. When ChatGPT makes a token, it might be like 1 or 2 tokens in, and it's producing those tokens purely based on the tokens that come before it. It's generative. It can't look into the future to decide what a token should mean. It can only look backwards. But BERT and other encoders are bidirectional. We take an entire block of text at once. It doesn't change, or we're not generating more text to add to the end of it. It's simply a paragraph that we're analyzing all at once. And a BERT is limited to 512 tokens, which is very small. This is probably not even one whole page of text. And you'll see that it takes a while. Not until 2024 did we involve modern BERT, an encoder that has a much larger context than that. So here's the basic process we're going to go look at in a moment. So quick brown fox is going to be our input text. We do have to tokenize that. I'll talk about that just a tiny little bit more when we're looking at it. And then we want to transition from tokens to through the encoder to get that dense representation on the far side. So let's have a look at this demo. Squint your eyes. It's going to be bright white. Okay, so here's my little playground that we're going to go through these different steps and do all the different demos. What I wanted to put in here is first we're going to tokenize it. And you can see like the way it breaks up your sentence. It may look very obvious with this sentence, which is just all common words. Each word has become a token. But what I'll highlight here is that there's a leading space, that there's actually tokens that the space comes before the word. And that makes sense about as soon as you think about it, because if a space was a separate token, it would basically double the token count of an English sentence, because there's spaces between every word. So learning that a space should come before most words simplified the tokenization. All right, what else can I show you here? If we switch to another model, we could see that there's other tokenization available. Do we have a Roberta in here? No, these are all the same word piece tokenizer from classic BERT. But we can put into here something like let's just put in some draft text from the slides. Let's try to really, what did we put in here? I put like a couple of bullet points, and when we tokenize this, we can start to see that some uncommon words, especially words that are capitalized, they are split apart. So there's no guarantee that a word is going to be a single token. In fact, I think you should mostly expect that an individual word is going to be multiple tokens. And this means that the model has like multiple places to apply its attention. It also means that the model can learn things about the singular version of a word that applies to its plural kind of automatically. And we have these control tokens that appear. The CLS token is going to be the class token, and SEP is going to be the separator token. So this class token gives us like something on the root. It's always the first token that appears in the sequence, and it allows the model to assign an embedding value that applies to the entire text as a whole. Meanwhile, the separator can be used to put in multiple texts together. And for encoders that are trained to respect the separator between texts, they can do what's called cross-encoding, where we look at both texts at the same time and think about on opposite sides of the separator how the texts are similar or different. And just to look at the tokens, you can see like some large words, especially custom words. The model may really not be getting a whole lot out of it because it could be a string of tokens that it doesn't really know from training. And that's one of the problems with these models, is if they don't know something from training, their output is essentially random, and it can be very confusing to determine which part of the output is nonsense because of a word that wasn't around when that model was trained versus actual confusion about the input it's getting. I think that's all I wanted to talk about for this guy, is just have a brief look at the tokenizer and look at the embeddings themselves, which is just hundreds of numbers that we can't directly make sense of. So let's try to make sense of those dense embeddings by looking at what we can do with them a little bit more. So the primary use case I'm going to demonstrate here is called a bi-encoder, and that process, when we tokenize a piece of text and then get that dense embedding out of it, that's something we want to do independently in a bi-encoder architecture, meaning we have text A and we get text B later. We're not encoding them both together, we're encoding them both separately. So the immediate use case for this is semantic search. So let's say that we have hundreds or millions of texts that we're going to encode. We save all of those embeddings in a database and search based on their vector representation. And then we can find other documents that are similar to those representations as a starting point for search results. So let's have a look at this guy, and we'll go to the encode tab. And first thing we'll see is that we have the tokens that appeared in this text. And of course, this embedding vector is, according to this model, 384 values long. And there they all, well, the first few of them are. Now we can have a look at this other text. And you can imagine like this demo is only set up for 2, but this process just encodes one piece of text independently. You can encode any number of them and put them in a database. And now we can compare the 2 tokens. The main thing we want to compare is cosine similarity. And cosine similarity is simply a comparison between the 2 vectors. It's sort of like what their angle is. This can be hard to wrap your head around in high dimensional space. But in something like 2D or 3D space, it makes a little bit more sense that if the first number turns, changes up a value or goes down a value, that vector is moving around, but the other dimensions aren't impacted. So cosine similarity is across all of those dimensions, not just 3 of them like in 3D space, but across 384 dimensional embedding meaning space. We are looking at these angles being this amount similar to each other. And the directions seem to be more important than the lengths in embedding vectors. The indication we're getting here is that these two things are similar. I don't know why. It's a very small model. I wouldn't put a lot of faith into its particular output here. But something I wanted to introduce here is that every token itself actually does receive a separate embedding. And this is important because now we can look at things like this token is bank. That's just the word bank, but bank has a lot of different meanings. We can see here that the bank by the river was muddy is referring to a bank as the side of a body of water, and referring to a bank here is referring to it as a financial institution in the second text. So comparing these, they have some cosine similarity, which we would expect to be higher when the words are sharing their sense and lower when the words are being used in a different sense. There's other ways that we can measure vectors against each other, such as the dot product or the L2 distance, where a dot product is just a kind of multiplication you can do with a whole vector of values all at once. And L2 distance is what you might call like the Euclidean distance, or the actual straight line distance between those 2 points, the points where the vectors end. And theoretically, if they are closer together, then they are in a similar region of semantic space and share some meaning. And if they're further apart, or that's similar of saying the cosine similarity, if their angles are very different, then they're probably have different values. All right, and we can do that with modern BERT as well. Unless you want to put in some really large documents, you probably wouldn't see much of a difference. A lot of common things, a lot of common strings really only have minor differences in tokenization. The reason to use something like modern BERT is if you have large context you want to compare. All right, so let's go into some of the more prediction-like capabilities encoders can give us. So we'll go into 2 different branches of what BERT evolved into. The first one is Roberta, and the RO is for robustly optimized. So that's robustly optimized BERT approach. And they basically did not change the architecture of BERT much of all. They did drop the next sentence prediction task, and they basically 10x'd the training data, but has the exact same 512 token context. Likewise for decoding enhanced BERT architecture. This used some disentangled attention techniques, which kind of in the world before rotary positional encodings managed to separate some of the content and position encoding that this model was doing. Meaning we're getting away from BERT's kind of naive or early techniques that couldn't really separate the position something was in versus the meaning of it. So words moving around, a word that means the same thing in a different place in the sentence should have a similar semantic vector, and disentangle attention is one way to work towards achieving that. But yet again, we did not go past BERT's original 512 token context. But these 2 models have plenty of fine tunes and different task heads that have been produced for them. And we're going to use some of each of these. I've kind of been mentioning this stuff here and there so far, but we have BERT, the basic one, Roberta, dBERTA, and then modern BERT. I think modern BERT has not really taken over the ecosystem yet. I think it will. I think it performs a lot better. And for example, like using flash attention just makes it much more performant than these older models. However, when you go looking for a encoder to do some kind of task, it's very likely that there's one already trained on one of the older BERT architectures that's ready to do that task. So modern BERT probably could do any of those things, but no one has bothered to retrain different task heads for it. All right, so let's talk about the cross encoder. The main premise here is that we're going to be providing two separate texts to the encoder at the same time. And this full attention between texts is what allows it to give a richer, more accurate comparison between the two texts. What comparison means is kind of specific to what task the encoder has been trained on. The most generic one is just similarity. Is this text related to this other text? But we'll also look at an NLI, natural language inference one, which is about if these texts prove, disprove, or are neutral to each other. The main drawback to the cross encoder value is that you can't pre-compute it. You have to select the text and perform cross encoding on the two texts together. This basically invalidates it as a standalone search technique. So the cross encoder is only used for re-ranking. We have to use a by encoder to find our coarse search results, and we use cross encoder if you want to refine them, because it would be impossible to cross encode your entire document database with every single query. So let's go play with the cross encoder. All right, so I'll actually pick the similarity one first. What we're going to do is just look at the way this thing loads the tokens into its encoder. So this is Roberta base. It's just a plain cross encoder, and it gives this similarity score for these two tokens. Now, the control tokens in Roberta are a little bit different. We have this kind of start of sentence, end of sentence token that show up here, and I'm just color coding here to show that the two sequences are both appearing in the context of the encoder at the same time, and we're extracting this value from the task head. Now let's go to the NLI version. This is a dBERTA model, and this NLI task it's been trained on is to provide a 0 to 1, or 0% to 100% certainty on these three labels: contradiction, neutral, and entailment. So the idea behind that is contradiction should be that the one text contradicts the other. Neutral means that the texts have nothing to do with each other, and entailment means that one logically follows or provides evidence for the other. So I might call these models a little jumpy to say contradiction kind of easily, but for an example here, we might say Sherlock Holmes is a genius versus Mr. Holmes failed his IQ test, and you would expect that to get a contradiction. Now let's say that he aced it instead and see if that figures it out. Yes, and that says entailment. So we can see that the model has very clearly learned something about acing IQ tests being associated with genius, and failing the test being the opposite of being a genius. And it can't generate new text, but it can tell us something about the text that's kind of useful in terms of search engines or classifying this text for certain purposes. All right, there's a couple more. So we did NLI, we did just some similarity cross-encoding. Let's have a look at the zero-shot classification as well. So this is a zero-shot classification example. The main idea here is you can take a hypothesis and cross-encode it with the input text and fill in a bunch of different labels into our hypothesis template. And whichever one cross-encodes as being the most similar seems like it's going to be the one that is the hypothesis we're going to go with. So what this example does when you execute it is it takes this text. I just bought a new laptop and it's amazing. That's our text A, and it cross encodes it 4 times with each one of these. It says this text is about technology. This text is about sports. This text is about politics. This text is about entertainment. And after we cross encode every one of those hypotheses with the original text, we get these different levels of similarity that give us the encoder model's output of, basically how similar or how related it thinks those two texts are. So the assertion here is that the similarity between a hypothesis and a input text that represents it could, at least for an encoder that is trained for that task, demonstrate just out of a bunch of different options which one is the most likely. All right, let's head on to the next capability domain. In this case, I want to talk about some more task-specific heads. Just the entailment and contradiction is a task-specific head. It's a classifier head. But I want to look at named entity recognition, which is, again, just another task head you can put on top of an encoder. And I specifically want to show span labeling, which is, in my opinion, one of the coolest things and one of the most flexible things you can do with an encoder that would let you take on new tasks with it. So here are some labels that we can look at, like an organization, a person, a location, or miscellaneous. And we're going to try to extract named entities that have these labels, and we're going to use a model specialized to do that. So we will go to extract, and I'm going to hit extract here, and I'll go straight to this labeling scheme. So we have the input text of Apple Inc. was founded by Steve Jobs in Cupertino, California. And what you can see is that we have extracted 4 entities from the sentence, and they are not represented by a single token. So this is using something called biotagging, and the B is for begin, I is for inside, and O is for outside. So the actual task that BERT base NER, which is named entity recognition, the actual task that this model is trained on is labeling every single one of the tokens with a B, an I, or an O. And the B is for beginning a sequence. In this case, all the B's have a specialization. So everywhere you see a badge, the token above it is this is a B org token. And this one is a B per, like beginning of a person span token. And every underlying token is labeled with an I. An I is for inside. So it's inside the span of this entity. And then every other token that has nothing under it, that's going to be labeled with an O, or an outside. Now, this is an interesting task because you can just imagine that there's all kinds of ways the model can predict invalid sequences, right? You can't have an I that just comes out of nowhere. You have to start with a B tag, have some number of I's, and then go back to O. And there's more advanced tagging techniques, but I also included like a binary one. And if you use this technique, what you see is like we're just labeling it as part of a span, and there's really nothing interesting that we can tell about the spans itself. You can imagine if we put in a different input that squished multiple things together, just having a binary identification of like, this is inside a span, this is not. Well, if the different spans actually butted up against each other, we would have no way to really split them apart, and this has already merged into a single entity. Although I don't know that BIO would actually handle this particular one better. No, it actually did smush them together too. But there are even more sophisticated ones that have different markers, not just BIO, but also ones for overlapping span labels. So But the named entity recognition is a pretty reliable and foundational task to demonstrate the capability. Now, there's a lot of things beyond classification that I just don't have time to make demos for every single one of these. I think another cool one is extractive QA. Like, just think about that span labeling system. Now, if we have a question and we have a larger text that includes like some background text, we can actually label a span that says this is the answer. We can't generate text, but we can select it, or we can highlight it out of a larger text. So that needle in a haystack capability is present in an encoder without even having a generative capability associated with it. All right, and just some last things to align with. There's a lot of other things to look at here, like keybert and BERTopic. Those models allow you to extract keywords. There's CLIP, contrastive language image pre-training. This is your bridge to get into multimodal. This is basically an image input to an encoder, and we get a dense representation, and that dense representation is in a shared embedding space that's also trained on text, which means we are basically learning text descriptions of images, or learning how to represent an image directly in the embedding space from text descriptions of that image. So if you see a bunch of keywords on images and those were applied automatically, the way it does that is it takes a lot of images and keywords, and we analyze the image. We force an image encoder to produce a dense embedding vector that aligns with the embedding vector of those keywords. And then later on, we can take new images and predict what keywords should be applied to it just from the embedding that comes out of it. There's also different domains like multi-language. You can train an encoder to specifically permit multilingual representations to have nearby semantic values, or specialized domains, because a lot of that technical jargon is going to be out of distribution for the simple models. If you want like deep code understanding, maybe try CodeBERT. And what if you had a task-specific head for an encoder that was a whole decoder, like a generative model? Well, now we are looking at something like T5 or BART, and these models permit you to take the language understanding in an encoder and immediately apply that to your decoder model, hopefully making them both very small. There's drawbacks, but that would be a whole other topic. It's very interesting, so if you want a video about that, hey, why don't you ask in the comments? So one thing I wanted to talk about was just the mindset I take to these sorts of things. I really hope to see these models be treated more as software components. I want you to get the confidence to pick them up and play with them. Think of them less like a scientific artifact, which is great, but it breaks my heart when some new model comes out and it's basically so entangled with the benchmark that it's working towards that there's no way to put it into inference. I would like to see things where I can just dump data into them and see what comes out of it. This is like the engineering mindset over the scientist mindset. So we are getting to that point. Just look at everything Hugging Face puts out with their transformers models. I encourage you to import a model, look at the interfaces, and if you don't like what you see under the hood, if it seems kind of tentacly or squiddy down there and it's just too dark and you want to ignore it, shut the box and treat it as a black box. I love a black box on a diagram. I love it when something is not my problem. So feel free to use these models without understanding what they do. Maybe try encoding a bunch of text and seeing what you can do in terms of search or similarity comparison that would, for example, let people type stuff into your RPG instead of requiring them to select from a list of fixed dialogue. That's one potential use for an encoder. It may not be terribly robust, but it probably would be fun to play with. So I'll get you all that stuff. And besides that, thanks for watching and listening.